Hi, in this video I want to show you how to use Ghidra to decompile a binary file. Okay, and I've already created here a Ghidra project, and our first step is now to add the binary file to this project. Okay, so let's do that. There's a menu, there is this import file. And the binary file is here on my computer, and we will import that one. So this is a special binary file. It's a raw binary file. This is a binary file that is unlike executable files that you know from Windows or Linux. So it's not an ELF file, or it's not a Windows portable executable file. It's really just a binary containing code and data. And such files you see sometimes when you are working with firmware, for example. Okay, so let's take this file. And now the format already, so Ghidra doesn't recognize the format and says, okay, this must be a raw binary file. Okay, this is already correct. Now we have to define the language. The language here means what kind of CPU this binary file, the code in the binary file was compiled for. And I know, because I know where this software is coming from, and usually know that for what kind of computer or for what kind of embedded systems this software was made for. I know that it's for an ARM CPU, version 5, and I know it's Little Endian. Okay, so I picked this one here. Now, if you don't know for what CPU architecture or this your binary file was produced for, well, you can try to find out what kind of CPU your embedded system is using, or you try some of from the big list of Ghidra has a big list of CPU architectures it understands, and you can try and see whether there's one where the output actually makes sense. Because if you pick the wrong architecture, you will see later in the decompiled code that it just looks like nonsense. But here we are lucky. We know that for version 5, some Little Endian. Another important thing is hidden a little bit here in this options button. And this is the important thing is this base address, because this is a raw binary, and usually raw binaries are made to be loaded at a specific location in your address space, or sometimes the binary is completely position independent. But you don't know that in advance. So just taking base address 0 is maybe not such a good idea, because on ARM CPUs and many other CPUs, things at address 0 have a special meaning. For example, many CPUs put their interrupt table vector tables at somewhere near address 0. So it's better, in my experience, to choose some other address. Now, we don't really know whether this firmware was made to be loaded at a specific address. Again, we can just try. You can pick an address and see whether the output makes sense. And I just type here some number here, which is far away from 0. And now, if you then decompile your code and you see a lot of strange numbers and addresses appearing in the decompiled code, that could be indication that this firmware was made, or this binary was made to be loaded at a very specific address. So let's try our luck. Okay, now we're done. Ghidra will then show you this dialog here that I had to move manually to my second screen. Okay, it's a quite small binary, yeah, it's just 208 bytes to make things easier. Okay, and now I can open it with a double click, and again I have to move manually the window that's opening now to my second screen, because Ghidra insists on opening it on my first screen, and I already clicked away a dialog. Ghidra is asking me whether I want to auto-analyze this binary file, but I just said no. Okay, and now you see the contents of the file, just a bunch of bytes, and you can see it's not a big file. Now there's a very high probability that this file contains not only code but also data, and this data might be even quite at the beginning. But we don't really know. So what we do is we just try and see whether we can disassemble. That means we can check whether this bytes here at the beginning are code or data. So we choose disassemble. And we position the cursor here on address 0, or not address 0, so offset 0 in the beginning of the file, and say disassemble. And you can see we are already a little bit lucky because this code here looks quite reasonable. If it was data, then this code might look like nonsense. But if you know a little bit of assembly language and machine instructions, this code kind of makes sense. So because you see no strange registers or constants or something like that. Okay, and actually what you can see here is a very good indication that what you see here is actually a function. Because what you see in this last line that Ghidra was able to disassemble is an instruction, is a kind of return instruction. Yeah? So program counter is restored from the stack. So this is a function probably. So we can just go here to the first line and tell Ghidra that this is a function. So we can call create function. And actually, if you look here on the right, the decompiler already is agreeing with us that this is a function. The decompiler already started decompiling this machine instructions, assuming that this is a function. Okay, so let's do that. Create function. Okay, and now you see on the decompiler turns white now because now we are in part of the code that we have officially declared as a function. Okay, but there is more stuff coming after this function, right? And Ghidra stopped disassembling because there were here some 0 bytes. Now, 0 bytes, you will see them very often. Often they contain data, or they are just some empty, unused bytes, padding bytes, to align the code to a multiple of 4 address or something like that. So let's just assume, or let's try, maybe this stuff here is also code. So let's put our cursor again here on the first byte here, not on 0 bytes. 0 bytes are probably not code. And disassemble again. And we are so lucky again. Okay, this is also code. And again, if you look at the decompile code on the right, Ghidra's decompiler thinks that this is a function, and I completely agree with that because what you see here in the first line here is our assembly and our machine instructions to back up registers on the stack. And here at the end, you see instructions to restore registers from the stack. So this is very typical for an ARM CPU or for any CPU to see this kind of instructions at the beginning and at the end of a function. Okay, this is probably also a function. So we put our cursor again here on the first line and let's create a function. Okay, so we have now 2 functions which contain a lot of machine instructions, and the decompiled stuff is also not very readable here. You see a lot of pointers, a lot of variables, but what do they actually mean? Good question. Now we have these 2 functions. You should start somewhere. What you can see already here in this first function, you can see here, if you look at the references here on the right, it's actually called by the second function here. If you double click on that, you see how the second function here is calling the first function. So maybe it's a good idea to start our adventure here with the second function here, so with this one. So let's see, what do we have here? Let's look at the decompiled. because probably many of you are not very familiar with ARM machine instructions. These are me, actually. So what do we see here on the right? We see that Ghidra is opinion that this function has 2 parameters. This is not necessarily right. Ghidra does sometimes make mistakes. But it thinks that. Why? Because it has seen that in the machine instructions, it's accessing register 0 and register 1. And these are typically the registers where ARM binaries are passing their arguments to functions that have less than 2 or 3 parameters. So Ghidra is probably right with that, that this function has 2 parameters. Okay, what else do we see? We see here some numbers, and these are addresses actually. Okay, you see them? Okay, we can jump to this, and you can see, these are just text. Okay, so this is a string here. So the first instruction is actually the address of a string, this number. So we can just, instead of showing this byte per byte, we can ask Ghidra to show it differently. And because I saw that this string was ending with a 0 byte, I just tell it to treat it as a C string. Okay, so you see in the decompiled window, it looks nicer. It's not showing the address anymore. It's showing the label that Ghidra has automatically assigned to this string here. Well, it's not showing the assembly window. It's only the decompiled window. And for the second address, it's the same. If you double click on it, you will jump here to this part here. And again, it's a string terminated with a 0 byte. So again, I will tell it that's terminated string. Often Ghidra is able to figure out itself that these are strings. At the beginning, Ghidra asked me whether I wanted to make an auto-analysis, and I said no. But if you had answered with a yes, Ghidra would be able to find the strings itself. Well, so in this way, it's more fun. Okay, if you really prefer, you can actually give this 2 strings here a label. We call this here the shop ID string, and I call this label here. I call this string here the page string. So it looks immediately nicer in the decompiled window. However, what's a little bit annoying is that Ghidra does not automatically do that in the disassembly window. Ghidra has not understood that this number here is actually an address. The decompiled window on the right, strangely, he has understood it, but not the disassembly window. So if you also want that here this number is not shown, instead it show page, this label that we gave to the string, you can actually force Ghidra to do that. For that, I said references and add reference from. And I choose memory, and I keep this address, and it's adjusted here. And now Ghidra understands that this address is actually a reference to the string below. And it's showing a label here. And I can do that for the other one. Here it is. Memory here. Okay. So let's turn back again to the decompile window. What can we see here? First of all, you see one of these parameters appears quite a lot of time, right? This parameter 1. And it always appears here with some number added. And when you see something like that, it's a very, I mean, why would you add so often a number to a parameter, right? Here, C, 10, 8. So probably this parameter is actually a pointer. And all these occurrences here where a number is added are probably offsets into a data structure. Yeah? So parameter 1 is probably a pointer to a data structure. We can tell Ghidra that. What we can do now is we can create a new type here on the left, can say create a new structure, and we can give the structure a name, and we can then tell Ghidra that this parameter 1 is actually a pointer to this structure. However, in Ghidra, we can actually do that automatically, what I just told you. We can just right-click here on the parameter and say auto-create structure. And now Ghidra will look at all the places where the parameter 1 was used and try to figure out what kind of data structure could be behind that. Let's do that, auto-create. And now you can see what Ghidra has done. Ghidra has automatically created a new data type, a structure, here on the left. If I click on it, you can see it here. This structure has 24 bytes. Okay. Well, it contains some stuff, some undefined fields, but the fields that Ghidra found in the compiled code and decompiled code are actually placed here. And you can see for some fields, Ghidra even saw that it's short, for example, a 16-bit integer. Okay, and you can see on the decompiled window that it looks much nicer now. Ghidra has declared that this parameter 1 is a pointer to this type, to this structure here. And now you can see it looks much more readable. Not bad. What else do we see? Okay, here in these two lines, you can see that functions are called. But there is no function name here, okay, or no address. Actually, the function address or function seems to come from a field from the data structure. That means this field 8 here seems to be actually a pointer to a function that is called here. And what kind of function could that be? Well, I mean, look, the parameters. The first parameter in both cases are these strings. And if you know C, you see immediately these are format strings. Okay, you see this %d here. So these are format strings. And there's a very strong indication. Look, that these two strings are format strings for some kind of printf instruction, right? Because you can see in the case where the string has only one format field, in that case, the function is also called with only one additional parameter argument. And for the page string, which contains two format fields, 2%d, the function is called actually with two additional arguments. So it's probably that's a very strong indication that this field 8 in this data structure is actually pointing to some print function. It could be also a format function that returns me a formatted string, but you can see here that there is no return value, it seems at least. So I will give this field the name. I will call it here printf. Why not? And let's look what else we see. Let's look at the arguments here of this. This printf function is actually not inside this code. Okay. Otherwise, we could now analyze it and understand how it works. This printf function seems to be an external function that is just passed up to us through this pointer in this data structure. However, we know that this format string is printing two integers or two 32-bit values. Now, these two values could be anything, right? We don't really know, but if I look here, let's say at this page here, my guess would be that the first number here is maybe the current page number, and the second number is maybe the number of pages in some document or something. So why not let's call this field here, why not call it page number. Okay, and the second one, well, this one seems to be the total number of pages. Well, how should we call it? Total page number? Let's just call it n. Okay, I will just call it n. Sometimes you see I'm not clicking here on the context menu. I'm just using the hotkeys. Okay, just call it n here. Okay, and for this field here, well, if you look at this job ID string, then maybe this is the job ID, so let's call that job ID. Okay. So let's look at the code here below. What you see here is some variables are initialized, and there's a loop here, and inside the loop, a variable is incremented by 2 in every iteration. And it's tested whether it has reached a value. So this is actually a clear pattern for a for loop, but Ghidra is just simply not smart enough to present it as a for loop. It's always using a while loop in the decompiled window. But I mean, that must be a for loop, right? You can see that this variable for is not modified anywhere in the code. No pointer is pointing to it is passed to any other function, anything. So this is probably a for loop, and this variable for is actually our iteration variable. So I will call it I. Okay. What's a little bit strange is that I is initialized to 0, which absolutely makes sense for a for loop, right? And it's incremented by 2 in every iteration. And when it's testing whether it has reached the final value, it's also multiplying the target value by 2. Why are they doing that? Why is the code doing that? Why is it not just incrementing this variable I by 1 in every iteration? You can see that here. I is not just counting in the for loop the number of iterations. It's actually used. It's added to another field of our structure here. Okay. And the result of that is used as a pointer. Now, when you see something like that in your code, a pointer is built by adding something to an iteration variable. This is really a clear indication that we have an array access here. So this field 14 here, or 14 in hexadecimal to be more correct, so is probably a pointer to an array. And we can even say what kind of array it is, because I is incremented by 2 in every iteration. So, and though this field is probably pointing to an array of 16-bit values. And Ghidra already actually knows that already. You can see it has written that this is a pointer to a short value. How does Ghidra know that? Well, you can see that here if you look in the assembly code. You see here a load instruction, and you see an H, the letter H at the end of the load instruction, or SH. This means this is an load instruction to load a signed half word, which in ARM language means a 16-bit value, a short. So this field 14 is probably an array. Now, sometimes Ghidra is very good in analyzing this kind of situation, and it will actually write this as an array access. But in this case, for whatever reasons, it's not able to do that. And you cannot really force it to print it like in the array notation. What I mean with array notation is sometimes Ghidra is able to write this as something like that, but not in this case. Okay, but we know that I'm quite confident that field here is an array, so let's just call it here some array. Okay, and for that we can also what kind of type has this field at the moment? Let's open the structure again, and you can see this at the moment, Ghidra thinks it's an int field, but we know that's not correct. It should be a pointer to an array. Okay, so let's save that. Okay, what else do we see here in the code? There's this other variable which is also initialized to 0, right? And you see it's incremented. You see I bar 3 is incremented by its own value, and these two other variables. So it seems that this variable is summing up something, and it is actually the result of the whole function. So let's call that here sum. Okay. The other two variables here don't seem to have some special meaning. They are just holding some intermediate results here. Okay. So I don't know whether we should give a name to that. Let's call them T1 and the other T2. Good. There is not really much more that we can do in Ghidra. Yeah, that's it, I would say. Yeah, here, there's one thing here. You can see that it's printing this code thing in front of the print of this function calls here. And this is because it's writing that because, look again at the data structure. We didn't really say that printf is a function. Unfortunately, in Ghidra, there is no data type that is saying printf is a function. What you can do is you can go to and define a new function type, and then tell the structure that this printf field is actually a pointer to this function type. However, with printf, you will have a problem, right? Because printf can have a variable number of arguments. In the first line, printf has 2 arguments. In the second line, it has 3 arguments, because printf has, yeah, you know that, right? The number of arguments of printf depends on the format string. Ghidra cannot really handle this. So what is often very convenient is that you just manually override. So you manually tell Ghidra, in this situation, this function has this signature. I will do that here. So I know that in this situation, it seems printf is a format string and 2 integers. Okay. But this is not really bothering much Ghidra. This is more for documenting for that yourself. Okay. And it's just writing a command here. And here in this case, it already figured out itself that it's the printf. Okay. So it's not really necessary here to do that, but sometimes it's convenient that you have documented that for yourself. Okay. What else? Well, we are mostly done here. Whatever this function is doing, we cannot go much further here. However, we can go to the function that is called here, which is actually the code here on the top. Let's go here. Well, Ghidra has figured out that this function has 1 parameter. Again, be careful. Sometimes Ghidra is not correct, but in this case, it seems to be right. Because if you look where this function is called here, if you look in the assembly, you can see that here, this I here is actually register 0. Let me see. It's register 5. So these are probably not any arguments here. Okay. The only argument seems to be this line here, register 0. This is where usually the first parameter of a function, the first argument of a function is passed. And parameter 0, Ghidra has figured out, register 0 is actually the same parameter that our first function or our function here has. So it seems that this big structure here that is containing all the interesting information, so it's printf and this array and this job ID and page number, is passed to the second function. So we can go to the second function and we can tell Ghidra that we know that this is a pointer to this structure that we had that Ghidra create. Okay. And now you see, now we know better that, okay, you see the same pattern here. Yeah, again, a function call using a function pointer. So we know that this field number 4, or this field at offset 4 in the structure, is also a function call. Okay. And it doesn't seem to be a printf or something. So maybe this time we are lucky, but we don't really know. But this time it seems we are lucky that this function is seems to be a normal function. So it has a fixed number of arguments. And if you look at the arguments here, you can see that the first argument is something read from a memory location. Okay, the memory location is actually here. This one here. The second argument is not a local variable, because this is local variable is identified as an array. It's a pointer to a local array, to a local variable. And the third parameter seems to be just a number. So this time I want to show you how to define a function definition. So let's say we say, okay, this function doesn't seem to have a return value. So we call this here function 4. And as I told you, this seems to have an int argument, the first one. The second one seems to be a pointer to something. The something here in the window is actually having 32 bits. But it could be also less. Don't really know. So let's just say void pointer. And the third parameter is number 2. It seems to be, when we int. Okay. Say okay. So we have now defined a new function, a new function type, and now we can tell Ghidra that this field here should have this function type. A very fast way is to just say a retype field, and we say, okay, this field number 4 is a pointer to this function definition 4. Okay, and you see it's printing it quite nicely here in the Decompiling window. That what we see here is that this function is called, and a pointer to some location on the an array of 5 short values is passed, and then when this function returns, we return the first element in this array. This is a little bit strange, right? It's quite difficult to imagine a function that takes an array of 5 elements, and then as a result, the result is the first element. It's possible, but I can tell you some information here. This code here was, I'm cheating here now a little bit, right? Because it was me who produced this binary. This code was produced with GCC compiler. Okay. And actually, this is a mistake. This is an inefficient, bad code generated by GCC. So actually, what I originally wrote in the original code was a local single short value. For some whatever reasons, GCC thinks it has to reserve 10 bytes for this local variable. You can see that in the machine code. And this confuses Ghidra. Ghidra thinks, oh, well, 10 bytes, that must be 5 short. So this is an array. But actually, it's not. But okay, if you see a firmware where you don't know the source code, you cannot really do much here. This is as far as you can get. Okay, again, why does Ghidra know that this is a short value and not an int value? Because if you look in the machine code, you can see that when returning the value, Ghidra is reading from memory, the machine instruction from memory, reading this value from memory is actually reading a signed half word, a 16-bit value, okay, which is then extended to 32 bits. And that's the reason why in the decompiled you see here a type cast to an int. Okay, that's it. So it's a very small example. However, you can see that thanks to the decompiler of Ghidra and thanks to our very sharp analysis, we have transformed the whole thing into quite readable code. You can see there might be still some things confusing in the code. For example, why is here an if and then this while loop? Actually, if you think about that, if you turn that into a for loop, you will take a sheet of paper and try to write that as a for loop. You will see that this if disappears. So this if together with this while, they are actually the equivalent code for a for loop. Okay, so this whole block is just a for loop. Yeah, if you now browse through the code here, you can see that we have basically decompiled or disassembled everything. What is left undefined is, for example, this field here, but this is probably some variable, because this is actually data reference. You can see that this is here, this data here, that is referenced in this line. And you can see here at the end of the second function, you can see here some bytes, which, well, we have not yet looked at them. What could that be? It could be machine instructions. So it could be actually code, but Ghidra didn't analyze them because they came after the end of the function. And well, we don't really know whether it's code or data. So what we can do is we can just try to disassemble it. Yeah. So we have done that. And what you'll see here looks pretty much more like nonsense. Why should be this kind of instructions in the middle of a binary between the end of one function and a string? So probably this was not really code. Okay, so I just do an undo here. This is just some bytes, maybe some data introduced by the compiler, or maybe it's used in some other module of the firmware, because this example I showed is very small. Okay, that's it. Now we don't forget to save your work, and what you can do now is there are several options. You could continue working on that. You can export what we have decompiled here to C code. We could export the whole thing as a binary again, which might be useful. For example, if you want to change something in the data. For example, you want to fix a string here. You could do that, of course, without Ghidra, right? You could just use some hex editor. But if you want to change an instruction, for example, that might be more useful. That's also possible in Ghidra. You could just say that you want to patch this instruction and change the instruction here. And then in that case, it would make sense to export the program as a binary. Okay, so effectively you have fully modified your binary file. Okay, that's all.